2026. Let me remind you that this is an activity organized by the Autonomous University of Barcelona, but we do it to share this with all the universities and research centers, not only in Barcelona, but also around the world for those people who join us. And this is just a cycle that wants to deal with the mathematics and machine learning and what machine learning can do for mathematics. We are very selective. We do that just 3 times a year. And we do it as mathematicians like to do, just with a lecture and then discussion and questions. And the most important thing for us is who are the people telling us about this interaction. And this year, we've had Hadi Shamir and Carlos Simpson. And today, we're very pleased to have Charles Fefferman. Charles Fefferman did his PhD in Princeton University and became a professor for a few years in University of Chicago, and then he went back to Princeton, where he spent most of his career, and is now an emeritus professor. In 1974, he was plenary speaker at the ICM. 1978, he got the Fields Medal, and among other prizes, in 2017, he got also the Wolf Prize. So now it's time for the math, and enjoy the talk.
Okay, well, thank you all for listening. I have a special thanks for Roberto for the kind introduction, and also for overcoming ridiculous internet technology issues. So he will actually be in control of the slides, and I will simply say from time to time, next slide, please. So thank you, Roberto. Okay, so the talk is about personal encounters with machine learning, and now we demonstrate how it works. Next slide, please. Thank you. Okay, so the talk will recount 2 old stories on results that are related to machine learning. The 2 results I'll discuss are completely unrelated, but the human element exists. Okay, next slide, please. Okay, so I hope you'll enjoy the stories, and I hope you'll not be put off by the fact that the results are far from you. Next slide, please. All right. So the 2 stories I'm going to tell are about the uniqueness problem for neural nets and about fitting smooth functions to data. The uniqueness problem I worked on in the 1990s, and the other I've been working on for the last 20 years or so. Oh, all right. So let's start. So the uniqueness problem for neural nets is the following. So next slide, please. All right. So I think in the audience there's probably no shortage of experts on machine learning, but I'm going to start at the beginning and just describe what a neural net is. There are many species of neural nets, but the simplest plain vanilla is the following. So look at the slide. We input, in this case, 3 real numbers. They populate the dots, the 3 dots at the bottom of the slide. Now, the 3 dots at the bottom of the slides send messages to the 2 dots in layer 1, and these messages are in the form of real numbers. Each dot in layer 1 processes the inputs it gets from the input layer and produces green arrows to the next layer. And what happens on those green arrows is that real numbers are sent to the dots in layer 2. Each dot in layer 2 looks at the green arrows feeding into it, processes the real numbers that are sent to it from layer 1, and produces a black arrow to the output layer. And the output layer finally processes the information from the dots in layer 2 and produces, in this case, a single output, a real number. So this is merely a special case. Of course, there may be many layers, not just 2 as in the slide. The number of dots in each layer, the number of inputs, the number of outputs, all of those are variable. That's a neural net. Now, in a little more detail, how does it work? Okay, next slide, please. So first of all, each wire is marked with a real number, which helps it to, which helps the node to which the wire feeds to do its processing. And furthermore, each node is marked with a real number. So the markings of the wires are called weights, and the markings of the dots are called thresholds. Next slide, please. And so what it does is the following. Suppose that you have a node. It's marked with a threshold theta, and it receives inputs x1 through xk from the wires that feed into the node. And those wires have been marked once and for all with the weights w1 through wk. Okay, so that's what feeds into a node. Next slide. And then what the node outputs is some function of the linear combination of the w's and the thetas that you see on the slide. And those are fed into some fixed standard nonlinear function, sigma. Sigma is called a sigmoid, or at least it used to be. And so that describes what a neural net does. So each node receives x's from the previous layer. It combines them using the weights w. It adds a threshold theta, and then that quantity is fed into one fixed standard nonlinear function, and that's what the node outputs to everything in the next layer, or perhaps to the outside world if the node happens to be an output node. Okay, next slide. All right, now which sigma shall we use? It used to be, anyway, when I worked on this problem, that there was a short list of popular sigmas, and high on the list was the hyperbolic tangent function. And that was popular because its graph looks the way every good calculus student should know, as shown on the slide. And this whole business was based on a loose analogy to the human brain. Okay, so in principle, that tells us what a neural net does. Now, there are lots and lots of neural nets. In particular, neural nets can have any number of layers. Each layer can have any number of nodes. And the whole thing, then the whole topology of the wires, the number of layers, the number of nodes in each layer, is called the architecture of the net. Next slide. Thanks. Okay, so a neural net is specified by its architecture and its weights and thresholds. Now, if you are an expert, you have already been bored to death. If you are a newcomer to this subject, let me just ask, is this clear? Would anyone like to hear any clarification on any point? Okay, let's move on. All right, next slide. So the uniqueness problem for neural nets is the following. If two neural nets do exactly the same thing, then are they essentially the same neural net? Well, more precisely, do they have the same weights and thresholds up to obvious equivalence, and assuming that they don't do anything ridiculous? Details to follow in the next slide or two. So, okay. So the first obvious equivalence is that if you permute the nodes in a given layer, of course, that has no effect on the output. And so that's one obvious equivalence of two neural nets. There's another. Next slide, please. Okay, so another obvious equivalence is that if you take a node which is neither an input node nor an output node, and if you change the sign of everything connected with that node, then all the minus signs cancel out, because the linear combination of the x's with the w's and the theta and all that changes sign. And then sigma is an odd function in this case, and therefore sigma of the stuff feeding into the node changes sign. But then the output weights also have a change of sign, and the whole thing cancels. And so that's another obvious equivalence. You can change a lot of signs without affecting the outcome of the neural net. All right, so those are the obvious equivalences. Now let's make sure that the neural net doesn't do anything ridiculous. So next slide, please. So an example of a silly redundancy is that if there are two nodes in the exact same layer and they use the exact same weights and thresholds, then there is no point including them both. They should have been combined. There are nodes with, let's say, 0 weights going out, so they have no effect on the output. There are silly things to do, which should obviously be avoided. And so, next slide, please. In order to avoid silly redundancies, we're going to assume that the ratio of 2 weights is never a rational number with a small denominator. Small depends on the architecture of the neural net, and I won't go into any details. This hypothesis has been greatly sharpened by a young mathematician graduated from ETH not so long ago, and I'm doing him a great disservice because I forgot his name. Let's move on. Next slide, please. Okay, so the uniqueness theorem is the following. Suppose that 2 neural nets, n and n prime, compute the same function and are free of silly redundancies. Then those 2 neural nets differ only by obvious equivalences. This solves a problem that was floating around in the 1990s. People were wondering about it. Okay, next slide, please. And so I would like briefly to describe the human element before I get to the ideas of the proof. People in this community, in the neural nets community, were aware of this problem. There was basically no progress. I heard about it, and I thought to myself, oh my God, this thing is so complicated, there is not a chance of understanding it. But it happens that a rumor circulated that the problem had been solved. And so suddenly I thought to myself, gee, it can't have been that complicated after all. It must have been simple. What simple idea could possibly crack it? And I thought of one, and it worked. And it turned out that the rumor was false. And so I had solved the uniqueness problem for neural nets. That's the human element in this proof. So now let's see the simple idea. So next slide. So the idea is analytic continuation. Namely, let's think about how the neural net responds to complex inputs rather than real inputs for which it was designed in the real world. No pun intended. Next slide, please. Okay, now without loss of generality, I'm going to assume that our neural nets have a single input and output a single output. And that's good because then we are dealing with analytic functions of one complex variable rather than analytic functions of several complex variables, which are of course much more difficult to treat. The reason you can do that is the following. So without loss of generality, there's only one output because you simply don't pay attention to any of the others. And then you understand the architecture and the weights and thresholds of that part of the net. Then you pass to the next output and do the same and so on. So you can look at one output at a time. And as far as inputs are concerned, let's assume that all the inputs except one are 0. And again, you can do the same thing. And so you can understand the whole thing if you can deal with neural nets with one input and one output. I'm hearing some voices. Does anybody have a question or a comment? Or is that feedback perhaps from my own voice? Okay.
I think someone had a mic open. I just closed it.
Oh, okay.
Okay.
All right. So functions of one complex variable. Okay, so let's move on. Next slide, please. Okay. Now our function, this sigmoid function, sigma of t equals a hyperbolic tangent, when we consider it as a function of a complex variable, has poles of an arithmetic progression in the complex plane, namely the odd multiples of pi I. And all right, in order to insult your intelligence, I have given in the next slide a picture of the multiples of the odd multiples of pi I. Next slide, please. There, the red dots are the poles of the function sigma. Okay, so what does that have to do? What influence does that have on the output of, let's say, a node in the first hidden layer? Next slide, please. Okay, well, if the input is t and a node in the first hidden layer has a weight w for the wire connecting it back to the single input node, and if its threshold is theta, then the output of that node is going to be, well, it's going to have a pole at those complex numbers t such that wt plus theta is an odd multiple of I pi, because simply the output is going to be sigma of wt plus theta. Okay, next slide, please. So, well, there are several nodes in the first layer, and if we look at all of the singularities of all of those nodes, we will get a picture in the complex plane something like this. And from that pattern, we can simply read off the first hidden layer. The spacings of the dots tell us the weights, and the horizontal placement of the dots tells us the thresholds. So if we could see this pattern, we could read off everything in the first hidden layer. But of course, nobody shows us this pattern. We would simply like to see it. All right, well, in a minute, we're going to look at the second hidden layer. So next slide, please. Let's look at a single node in the second hidden layer. Now it receives inputs x1 through xk from the first layer, and then it outputs the sigmoid tanh applied to the usual quantity that you see on the slide, and the x's are the outputs of the first hidden layer. Well, all right, so we're going to be interested in the singularities of that function of a complex variable t. Again, the x's are functions of t. We feed them into this linear combination and then take the tanh. What are the singularities of that? Next slide, please. Okay, well, let's say that T0 is one of our poles of a layer of an output from the first hidden layer, let's say from the first node of the first hidden layer. So T0 is a pole of x1 of t. Now, with any luck, there are no evil coincidences, and T0 is not a pole of any of the other nodes of the first hidden layer. And therefore, when you look at the linear combination before you take the sigmoid, if you look at the W1 times x1 of t plus and so on, plus wk of xk of t plus theta, that's going to be, as shown on the slide, lambda over t minus t0 plus an analytic function of t. That's what happens near t equals t0, because the only thing that is singular is the first term, w1 x1, and so that's what it looks like. Okay, next slide, please. All right, therefore, the output of the node in the second layer will have a pole at values of t for which this quantity, lambda over t minus t0 plus some analytic function, is an odd multiple of pi I, because that means that the quantity at which the sigmoid is evaluated is just right to produce a pole. Okay, next slide, please. And so that means that we have the following picture of the outputs of the nodes in the second layer. So we have the green dots. The green dots are the poles of the outputs of the first hidden layer. And then we have, let's see, what color have I got? We've got red dots. And we have, for each green dot, I've drawn 3 series of red dots. Each series of red dots represents the values that give rise to an arithmetic progression as on the previous slide, but from one of the layers, from one of the nodes in the second layer. And in this case, there are supposed to be 3 nodes in the second layer, and therefore there are these 3 series of red dots for each green dot. And so if you look at all of the outputs of all of the nodes in the second layer, the red dots would be poles and the green dots would be essential singularities. And so if you could see this picture, you could read off both the second layer, everything about the second layer from the red dots, and everything about the first layer from the green dots. That's if you could see this pattern, but of course no one shows you this pattern. You have only a neural net and its input to output map. Okay, so let's move on. Next slide. All right, well, we keep going and let's see, we continue in this way. So the thing is that at the very end, when we look at the function computed by the neural net, all of a sudden we can see it, and we will see a picture that has singularities in the complex plane, like the next slide. So please, the next slide. Next slide, please. Oops, what happened?
Yes, I have to come to the second file.
Oh,
the
okay.
slides, and I think this. That's let me see now.
All right, pardon the ringing telephone. I assume it will stop in a minute. Okay, so here finally is some approximation to what the singularities will be for the final output of the neural net. So we have a series of what I thought were green dots. I have a feeling that maybe color has been suppressed here. Anyway, we have a series of green dots. Those are the arithmetic progression arising from the first hidden layer. And then we have, for each green dot, we have a series of red dots moving in toward it, and those reflect what's going on in the second hidden layer. And then for each of those dots, there is a series of black dots, and those represent what's going on in some third hidden layer. And so something like this is the full picture. Ah, there it is. Wonderful. Thank you. In excellent color. Okay. So this is now a picture of the singularities from the output layer, and from the green dots, you read off what's happening in the first hidden layer. From the red dots, you figure out what's happening in the second layer. From the black dots, in the third layer, and so on. Perhaps there are additional layers. I ran out of artistic ability and patience, but you get the picture. And so this is the picture of the singularities of the output of the neural net, and therefore we do get to see it, at least if we could do analytic continuation. So this is uniquely specified by the input to output map of the neural net, and we can read it off, and that allows us to read off the complete specification of the neural net, its architecture, and its weights and thresholds. Next slide, please. And okay, well, all right, I've already said that. So, okay, next slide, please. Of course, this is only an intuitive discussion. Remember, it included the phrase "with any luck." So we have to work in order to make a rigorous proof of this, but let's enjoy the lecture and suppress the effort and just believe that if you put in a bit of work, you can actually make this discussion into a rigorous proof. And so that is the solution of the uniqueness problem for neural nets. Of course, it would be nice if you could actually use that to build neural nets that have a given input to output map, but that's hopeless because analytic continuation is a very unstable process, if for no other reason. But we've solved the uniqueness problem for neural nets. Okay, let's move on to the next problem. Next slide, please. Okay, so now we're fitting smooth functions to data. Now, so what I have in mind is that these functions are going to be defined on Rn. Rn, for our purposes, is not too big. But we have a lot of data, and it means that there is a large finite set of points in Rn, and for each of those points, we are given a function value, maybe exactly, maybe approximately. In this talk, to keep everything simple, we'll assume that we're given exact values. So we have finitely many data points. At each data point, we have a prescribed function value, and we're trying to fit a smooth function to data. Now, what does smooth mean? Okay, next slide, please. Okay, so to specify what smooth means, let's say X is our favorite Banach space of functions on Rn. I should say that it should consist of continuous functions because we will be evaluating those functions at a point. And so maybe X is Cm of Rn, M continuous derivatives. Maybe X is a Sobolev space, WMP of Rn, maybe M derivatives in LP. Maybe X is Cm alpha, derivatives up to order M that are Holder of order alpha, whatever. And for each X, there's a different flavor of the problem. In this, all right, in this talk, I'm just going to look at Cm of Rn, M continuous derivatives. So for our purposes, all right, we're working in Cm. So our problem is, okay, next slide, please. Yes, given a finite set, possibly a very large finite set in Rn, and given, let's say, a real valued function on that large finite set, we want to find a function capital F in our favorite Banach space X that agrees with the function little f on E, but with its norm in the Banach space X as small as possible or nearly so. That's the problem. Now, to find this function, I have in mind that we want to compute it using a computer. And so I want to, again, I want to suppress technical details. I won't say what the mathematical description is of a computer. Just think of it as what von Neumann would have recognized. Okay, next slide, please. Okay, we would also like to find the least possible norm of the function capital F computed before. That tells us whether it makes sense to fit the data to a smooth function or not. So, for example, consider the two pictures in the slide, one labeled good, the other labeled bad. These are graphs of functions of one variable, and so the green dots represent both the set E and the function little f. In the upper picture, it's clear that it's a good idea to try to fit the data to a smooth function, whereas for the second picture, it's a bad idea to try to fit the data to a smooth function. And you can tell that because the least possible norm in the upper picture is going to be reasonable, and the least possible norm in the lower picture is going to be unreasonably large. Okay, next slide. Okay, simple examples show that this inf of the norms of interpolants may be an inf, not a minimum. The minimum may not be achieved. I mean, one can see that in very simple examples. So we're going to make a couple of definitions to cope with that. Next slide. Okay, so first of all, for a function little f defined on a finite set in Rn, I'm going to say that its norm in x of E is the inf of the norms in X of all possible functions capital F that agree with little f on the set E. So that's the norm. That's the inf that we're trying to achieve. Next slide. And then for a constant A, presumably strictly greater than 1, an A optimal interpolant is, for a given interpolation problem is a function capital F in our Banach space that agrees with the data, capital F equals little f on E, and its norm in X is within a factor A of the inf of the least possible norm, with the understanding that that least possible norm may not be achieved. So that's the notion of an A optimal interpolant. And so we want to compute with a computer an A optimal interpolant. Next slide, please. Okay, so our problem is, given a function on a finite set E, a real valued function, compute an A optimal interpolant with A, this constant, depending only on the space X and not on the particular interpolation problem within the context of the space X. That's the problem. Now I say compute. We're supposed to compute a function, and yet we're supposed to use a computer. Now a computer can hold only a finite number of real numbers. In fact, it can't even hold one real number perfectly. It holds finite binary expansions of real numbers. Let's not get into that technicality now. Let's say a computer can hold a finite number of real numbers, and yet a function capital F is definitely a bigger object than that. So what does it mean to compute a function? Well, next slide, please. Okay, so computing a function means the following. So I'm going to explain what it means in the case that our Banach space is Cm of Rn. So our function f is going to have m continuous derivatives. So imagine we sit at a computer and we enter the data. The data consists of the set E and the function f. The computer then performs one-time work, after which it can answer our queries. All right, next slide, please. I'm going to describe what a query is and what the computer is supposed to do with our query. So a query consists of a point, x hat in Rn. And the response to a query x hat consists of the function value and the values of all the derivatives of that function up to order m at x hat. And so if the computer is computing the function capital F, that means that when we enter the data, it does its one-time work and then answers our queries. And for any query point x, the response to the query correctly describes the function f and its derivatives up to order m. And of course, we can't ask for more information than that because the function only has m derivatives in principle. Next slide, please. Okay, now we want efficient algorithms that make minimal use of the resources of the computer, and the relevant computer resources are shown on the slide. They are the number of operations needed to perform the one-time work, the number of operations needed to answer a query, and the size of the memory. Now, we only need to do the one-time work once, hence the name, whereas we probably are going to pose a lot of queries to the computer. And so maybe it's more important to optimize the query work than it is to optimize the one-time work. And so one might expect trade-offs when you're trying to optimize 3 resources, but a pleasant surprise is shown on the next slide. Next slide, please. So we're going to optimize all those resources simultaneously. No need for trade-offs. Next slide, please. Okay, so there is an interpolation algorithm for the Banach space Cm of Rn. It's joint work with Boas-Klartag. Again, our Banach space is Cm of Rn, and the algorithm performs as follows. Next slide, please. So given an interpolation problem, so given a function, a real valued function on a great big set in Rn with capital N elements, we're going to compute an A-optimal interpolant using the following computer resources. O of n log n one-time work, O of log n query work, O of n memory. Here, that constant A depends only on little m and little n. Those are the parameters that specify which Banach space we're working in. So as in the statement of the problem, capital A depends only on the space in which we measure smoothness. Now let's think about these numbers. First of all, O of n one-time work. Probably it would be a good idea to read the data. The data consist of capital N numbers. So there are at least, the work required is at least capital N, and up to a logarithm, we've already got that. And one can also pose simple problems in which it would appear that O of n log n work is already needed. How about the query work? So we pose a query, the computer answers the query. Presumably the computer is doing something to figure out the answer, but regardless, the computer should probably read the query and it should probably print out an answer. That's work at least 2. And the query work here is within log n of that. And again, there are particular problems that would appear to the naked eye to require log n work. And finally, O of n memory, that's rock solid. We had better remember the problem, because if I ask you for the value of an interpolant at one of the input data points, it had better be spot on, and so we had better remember the data that's memory n. That means it can remember n numbers. Okay, next slide, please. So the algorithm is theoretically optimal. Unfortunately, it is not of the slightest practical use because this constant A that depends only on the choice of the Banach space is too big. And so I've wondered for a long time, can the proof of that the algorithm works be tweaked in order to yield something practical? And well, getting anything of practical use is a tough problem, so I wouldn't a priori be terribly optimistic, but hope springs eternal, and so I pose the question. In particular, the reason that A is too big lies in the proof of one particular lemma, and so if that lemma can be tweaked to provide a less enormous A, then we're in good shape. And in fact, it has been tweaked to provide a less enormous A by a team involving, I think, Aryeh Israel and Boas-Klartag and a couple of other people. I'm sorry, I don't remember the names, but A is still too big for practical use. Okay, next slide, please. No time to explain the algorithm. Yes, no time. But there is something worth saying, I think, which is that the algorithm is based on the proof of an interesting, simple conjecture with an interesting history. And so instead of explaining the algorithm, I'm going to tell you about the conjecture and its history. Next slide, please. So the history of the conjecture starts in 1936 with Whitney's extension problem. So Hassler-Whitney wrote a series of papers on this problem in 1936, very influential. Well, let's state the problem. Next slide, please. So here's Whitney's problem. So we fix little m and little n, positive integers. We're given a function from E to R, but E is not a finite set. E is now a compact set, possibly very pathological. And the problem is to decide whether little f extends to a CM function, capital F, on the whole Rn. What can we compute? How can we tell? That's Whitney's problem. Next slide, please. Okay, now that problem wasn't solved for a long time. It was finally solved in 2003. But in 1936, Whitney already solved an easier variant, which I will now state. Next slide, please. Okay, so for the variant, we fix positive integers m and n, and again, we're interested in CM functions on Rn. Again, E is a compact set, but now for each point of E, we don't merely specify a function value, little f of x, but instead we specify an alleged Taylor polynomial of degree m. So for each point x in E, we are given an mth degree polynomial on Rn, which is called px. And the problem in the red box there is, how can we tell whether there exists a CM function such that at every point x in E, px is the mth degree Taylor polynomial of f at that point x. I'm afraid that there's a misprint in the box. I didn't say at x, but that's the problem. So instead of specifying a whole lot of function values, we specify a whole lot of Taylor polynomials. Next slide, please. Okay, and so in 1936, among other things, Whitney published the Whitney extension theorem. The statement of that theorem, well, I won't give it in technical detail, but it tells us that the obvious necessary conditions are already sufficient. And the obvious necessary conditions are simple consequences of Taylor's theorem. If you know, if you're given a CM function, and you look at its Taylor series at, let's say, at 2 nearby points, those Taylor polynomials had better be close. Okay, and so that's the Whitney extension theorem. Next slide, please. Now, the proof of the Whitney extension theorem had very far-reaching consequences in analysis that I'm not going to talk about. But for our story, I am going to focus on one of the consequences of Whitney's proof of the Whitney extension theorem, and it has to do with 2 Soviet mathematicians in the 1970s and 1980s. Next slide, please. Okay, and so now again we come to the human element. The characters in the drama are the Soviet mathematicians Yuri Brudny and Pavel Schwarzman. They were working in the Soviet Union in isolation. It was difficult for them to get access to the Western mathematics literature, but they heard a rumor that Whitney had done important work related to the Whitney extension problem. And so they decided that they would reconstruct, they would try to reverse engineer, given that information, what it is that Whitney had done. And they came up with something very interesting, but they guessed wrong. It had nothing to do with what Whitney did. Instead, it was a finiteness principle, which I will now explain. Next slide, please. So here's the simplest version of the finiteness principle. So now we're again looking at functions defined on a finite set, E, real valued functions. This time, let's say the points of E lie in the plane. So E is a large finite set, and we want to extend little f to a C2 function, capital F. Suppose that for every 6-point subset of the data set E, there is an interpolant, which we're going to call capital F sub s, which agrees with the data. So capital F sub s is equal to little f on the set S, and yet its C2 norm is at most 1. Okay, So we're trying to solve a big interpolation problem, and we're assuming that we can solve all of the little 6-point subproblems with a common bound on the C2 norm of the interpolant, namely 1. Next slide, please. Well, if you can do that, then there exists an interpolant for the whole problem. So there is a function capital F in C2 of the plane, which agrees with the function little f on all 50 billion points of the set E, and yet the C2 norm of this function capital F is less than or equal to a universal constant, which is actually not so big. So that's the simplest version of the Brudny-Schwarzman finiteness principle. Next slide, please. All right, now the same holds for C2, not only of the plane, but of Rn, and the strange number 6 is replaced by the strange number 3 times 2 to the power n minus 1. That number is sharp. If you replace that number by one less, then the theorem becomes false. So there's a completely sharp criterion for the existence of an interpolant with a reasonable C2 norm. Next slide, please. Okay, the proof by Brudny and Schwarzman doesn't extend beyond C2. They have various results, which I'm not going to state, but they stop. I mean, they don't attack anything smoother than C2. But Brudny and Schwarzman nevertheless made the natural conjecture, given what I just told you. Next slide, please. So the natural conjecture is given two positive integers, m and n. There is a positive integer k sharp playing the role of 6, or 3 times 2 to the n minus 1, and it has the following property. Suppose I give you a function little f on a finite subset of Rn. By the way, the subset has to be finite. The analog for infinite sets is false. Suppose that for each little subset S in E, where little means that it has at most k sharp points, there is an interpolant, capital Fs, in Cm, agreeing with the data on the set S and having Cm norm at most 1. Next slide, please. So assuming all that, then there exists a capital F. There is an interpolant in Cm that agrees with the data on, whoops, there's a misprint. It should be on the set E. So it solves the whole interpolation problem, and yet its C2 norm is at most a constant that depends only on which space we're working in. Our space is Cm of Rn, and so it depends only on little m and little n. And so that's just the natural extension of the Brudny-Schwarzman finiteness principle for C2 of Rn. They conjectured it for Cm of Rn. Okay, next slide, please. Okay, now I worked on that conjecture and I proved it in about the year 2002. And the ideas in the proof of that conjecture are the starting point for the interpolation algorithm that I mentioned before, that solves the problem of fitting a smooth function to data. Okay, and so I think that's all I should say about technical matters. Now I would like to explain my view of the link between these two problems, whose mathematics are entirely unrelated. So the link lies in the human element. Next slide, please. So the moral of the story is that inaccurate information can promote scientific discovery. In the first case, for the neural nets problem, I heard that the problem had been solved. That turned out not to be true, but the fact that I heard the rumor was the key that allowed me to see the simple idea. And in the case of Brudny and Schwarzman, the fact that they knew that Whitney had proved something but didn't quite know what led them to formulate their finiteness principle. And if instead they had had let's say, access to the archive, they would immediately have known what Whitney had proved, and the finiteness principle would be undiscovered for a long time. So inaccurate information can promote scientific discovery. That's the link between the two topics. Next slide, please. We are constantly surrounded by inaccurate information. May discovery thrive. Next slide. Thanks for listening. That's it. Oh,
Okay.
see,
Thank you. Thank you for the talk. And now it's time for questions and discussion. And if someone wants to ask something about any of the two problems or about the moral.
Or if anyone would like to provide inaccurate information.
Yeah. Yeah. Okay, we have a question. Yeah, two questions. First, Egor, please.
Hi. Yeah,
Hi.
amazing talk. Thank you.
Thank
Can
you.
you hear me?
Yes, I hear you.
Yes.
I can barely see you. You are a little black rectangle, but I hear you.
Okay, here it comes, I think. So, yeah, no, I just wanted to. There was this story about one graduate student at MIT who came in late to the lecture, where the professor puts like some problem, which he said was unsolved, but the student didn't hear it, right? And thought it was a homework, and then he came back and solved it, basically with inaccurate information. I don't quite remember the name, but it's a famous example of the same principle.
I see. Well, thank you. So, okay, thank you. That supports my central point. Thank you.
I'll try to figure out the name.
Yeah. I wonder if the information you've provided is accurate. We don't know.
I'll search for it now.
Okay.
Okay, thank you. We have also Joan.
Oh, okay, but Igor, please come back to us if you find. Okay.
Okay. Okay, I am Janorovich. I don't have any question for your talk. Only to thank you for giving this talk in this seminar, what is organized by Roberto Rubio, and he's from the Autonomous University. And then there are many people here in the mathematical group, no, that know very well the results of Fefferman, of Charles, who are working in the 70s and the 80s, no, when you are working with Hardy spaces and you have many results with some other contributions like Stein, Koisman, and now we're very happy to listen to you. And okay, then we are only to say hello and thank you for your talk, and always thankful for your nice results and your great contributions to harmonic analysis and so on. Thank you, Charles Fefferman. Okay.
Well, thank you for those very kind comments. Thank you. I hope you have enjoyed the talk. You can see that I designed it with the idea that it should be fun rather than a strain.
Okay, thank you. We have also Van Hirup.
Yeah, so I think the mathematician that Igor was talking about, I think is George Dantzig.
Oh, do you happen to know
Yeah.
what the problem was that he solved?
No, I don't remember. It was some
Okay.
famous conjecture. Yeah.
Wonderful. All right. So I guess the obvious thing to say is that I've just heard that the Riemann hypothesis has been proven. Okay. Right. There's this. Okay. Let's leave that there. Okay. But so the story about the mistaken homework problem that led to the solution, etc. That's all true. Wow.
Yeah. He was that time he was in Berkeley, I think, as a doctoral student.
Oh, wonderful.
Yeah.
More questions, comments? I do have a couple of questions at least. I would like to start with your first story. You kind of created this kind of, I don't know, more of a point code of the neural network, right? By looking at the poles. of
Right.
when you see it. Yeah, okay. So I was wondering, among all the hypotheses you put, some of them were really like, say, obvious that, okay, we shouldn't just repeat a node, and then you can see how you will get the same poles, right? But there was one that you discussed, and now perhaps I'll go back to the slides to show it, that actually you said it had been sharpened later
yes.
on, which was this thing of this rational, the ratio and so on, depending on the number of nodes. And I wonder if you could relate that to this drawing you showed us.
Oh,
Yeah.
yes, sure. All right. So maybe come back to the picture.
Yes, I will go there in when this allow me to go there.
Sure.
Okay, the picture, shall I, like the last picture you showed with all the green, the red, and the black, is that good enough?
Sure,
Yeah.
that's fine.
Okay, so just a second.
You know what? Wait. Maybe
Or-
the second picture with only red and green dots.
Okay,
Maybe that
so
makes
yeah,
things clearer.
so just a second because it's in a different file, but I'll be there very soon. Okay. Okay, so this is the file. Is this the one?
Yes. Okay.
Yeah.
So remember that picture comes from the idea that you have one node of the first layer, and we're close to a pole of the output of that guy, and the claim is that with any luck, the other nodes in the first layer don't contribute anything significant. The danger that might invalidate this picture is that let's say there are 2 or 3 nodes of the first hidden layer which have a pole at exactly the same point, and then the output weights are are um, are contrived with evil intent so that the alleged singularities simply cancel out and there is no pole. Okay, that has to be ruled out, and that will be ruled out under appropriate hypotheses about rational ratios, etc. What happens is that some of the green dots may be subject to evil cancellations, but most of the green dots will survive intact, and that story continues up to the higher levels. And so one has to define an almost arithmetic progression rather than an actual arithmetic progression. And so it is allowed to have some missing dots, and also it should not be an exact arithmetic progression, but at infinity it should be asymptotic to an arithmetic progression. And one talks about the approximate union of approximate arithmetic progressions, in which, again, you take the actual union, but you are allowed to delete some dots, and so on. And all of that is good enough to make the intuitive picture rigorous. Now, that was somewhat lazy on my part. I assumed, again, wrongly, that to keep very careful track of exactly which cancellations might actually occur would just be too complicated. And so I made this assumption. But the PhD student at ETH, oh God, I should have looked him up. I actually made the careful discovery, and I don't want to phrase it as if he simply put in extra work. He put in ideas. One can make a very sharp version of this theorem in which, for example, one does not worry about rational ratios of nodes of weights. Also, the notion of a neural network is more general than I've indicated. The classic plain vanilla neural network has nodes arranged in layers the way I described, but one can take a more general version in which the nodes simply form any acyclic graph, and the input, you input, you produce inputs at some nodes, and the net processes them by running them through the graph, and then at the output nodes you get a result, and the analytic continuation of that allows you to recover the acyclic graph and all of the weights and thresholds. The silly redundancies that are ruled out are given very explicitly, and they are indeed silly. For example, your acyclic graph could include a node that outputs to nothing. Okay, well, that shouldn't happen. There should not be two nodes that do exactly the same thing, that get exactly the same inputs and produce exactly the same outputs. And I think that's it. And the changes that you're allowed to make are precisely permuting the nodes in the graph in such a way that the two graphs are isomorphic as graphs, and making sign changes. So it becomes a very sharp result. If you like, I can, after the fact, look up who this fellow is and send you an email with.
That would be great. Yeah. Okay. Yeah. Sure. So and I have another question about the design, the second part. So I have to now let me show the screen.
Okay.
Hopefully, it's about this 3 times 2 to the n-1, because
Yes.
you said somehow like yeah, at first I thought, yeah, it was going to be just okay, something that you could do well, but then you said no, actually you cannot do any better. It's a sharp bound.
Yeah.
So
Yeah.
and I was wondering, in the simplest case of 6, whether there is a like would be 5, right? Like, do you have a
Right.
very simple example where with 5?
Oh, there is one, and I'm sorry, I don't remember it. This is, I studied this in 2005 or so, or no, 2002. I'm sorry, I just don't remember. There is a very simple example with 5 dots, where you could yes, there is. Okay, no, all right. At least I remember what it is. There is an example of, although I do not remember the example. So there is an interpolation problem involving 6 dots, and so you have a 6-point set in the plane and a real valued function giving each, carrying each of those 6 points to a real number. You are looking for a C2 function in the plane that takes the given values at the 6 dots, and for any 5 of the dots, you can make an interpolation with C2 norm 1. However, if you want to cover all 6 dots, the best you can do is arbitrarily large. Now, what does that mean? It means that in an example of 6 dots, and of maybe functions and all, the problem depends on, let's say, one parameter. And as you vary one parameter, you find uniformly every 5 dots can be solved with a uniform bound on the C2 norm of the interpolant. But if you are trying to solve the problem for all 6 dots, the best C2 norm you can achieve depends on the parameter and tends to infinity as the parameter tends to infinity. Okay, so that's the nature of the example, and I don't remember the example.
Okay, and 6, why these 3 times to the 2 to the n-1?
Oh, thank you. I can give a very precise answer to that question. No, I have no intuition. Let's see, one of the 2 characters I mentioned, Pavel Schwarzman, has a conjecture as to what the best constant should be as a function of little m and little m of Rn. Enormous. For C5 of R10, the number has many, many decimal digits. This is I have asked him what is the intuition behind that conjecture, and he cannot, or at least does not, tell me. So I could just report that there is a conjecture, and even in the known case, I have absolutely no idea why this number should be the best possible.
Okay. Okay. Thank you for the answer. Yeah.
Thank you for the questions, and
Yeah.
also thank you for yeoman service moving the slides.
No, yeah. We have still, I don't know if someone else has another question or comment. Because I do have, you see, we have in this cycle, I don't know if you looked at the list of speakers, like we really, yeah, thrive for this profile of a mathematician who at some point, or at 2 points, say, got interested into machine learning. So it would be great if you could share with us somehow how you have experienced this interaction and whether it's something, very anecdotal in your career or very, don't know, something about how it's been and somehow how come you enter one time, you did that, and then you came back later on to this sort of fitting the data.
Oh, sure. Okay, so well, in general, I like mathematical problems that have something to do with the outside world. The problems may or not be practical, but they should, if they have nevertheless somehow some resonance with the real world, for me that's a big plus. Now, all right, for the neural nets problem, simply I made friends with a mathematician named Norm Winarski, who was working at Sarnoff Labs, which at the time was located just outside Princeton. And he told me that they're working on this really interesting subject, neural nets. Why don't I come over and talk to them? And I did. So I consulted there for a while. And so I heard about the problem, and I mean, and the rest of the story, you know. So that's how I got involved with neural nets. As far as fitting smooth functions to data, what happened was that first, as a grad student, I learned the Whitney extension theorem. I thought it was a wonderful theorem, and I thought that solved the problem. But then I met Brudny and Schwartzman in Israel in the 90s, and they explained to me that no, Whitney's problem was not solved by the Whitney extension theorem, and they had this finiteness principle, which in fact I forgot about. But I remembered that there was the problem. I then in the year 2000, I heard a lecture by Ed Bierstone from the University of Toronto, who was at Princeton for a conference, and he lectured on another ingredient of Whitney's problem, which I didn't talk about. So ideas not obviously related to the finiteness principle, but that sparked my interest in Whitney's problem, and from that moment for the next, I don't know, 20 plus years, I couldn't stop thinking about it. It led me back to the finiteness principle, and after working on this for a while, it occurred to me, well, wait a minute, suppose our set is the set from which we're trying to extend is finite. Of course, if you have a function on a finite set, of course it extends to a CM function, but how small is its norm? And let's do something a little better than the usual introductory math trick in which you introduce a spike at each point and just take that linear combination. What's a sensible way to interpolate, and how many computer operations does it take? And well, if let's say if every 6-point set is enough, presumably that means that n to the 6th power operations should be enough for C2 of the plane. That's all. I mean, it's polynomial time, but that's already a lot. So, all right, I then made enough progress that I was able to get n squared operations for Cm of Rn, and I was very excited. But fortunately, one of the people sitting in on my graduate class was the young Boaz Klartag, an amazingly smart fellow, who showed me that no, we can get n log n for at least for the order of magnitude of the norm, and then we collaborated and got n log n for the interval itself, and we collaborated I would say intensively for a few years, and very, very sparsely after that. But that's the story. In addition to that, I have other interests in machine learning. I met the then young Hariharan Narayanan, who was then, I think, a postdoc working with the engineer Sanjoy Mitter at MIT, and they explained to me about manifold learning. And we produced a paper called Testing the Manifold Hypothesis, in which we produced an extremely labor-intensive algorithm, which, however, tests the hypothesis that data in a high-dimensional Euclidean space can fit reasonably well to a low-dimensional manifold with reasonable geometry. Although that algorithm is much too labor-intensive to be practical, nevertheless, at least it was an algorithm that tested a very widely used hypothesis. And so I see from my email every morning that people continue to quote that paper. There are other, I have other interests that are related to machine learning, but I think maybe I've spoken too long.
No, I mean, if you could just like announce them like you did with this one, would be great to have like if you want to mention.
Okay, sure. So I'm working. Sure. I'm working now with a couple of Princeton grad students, Jonathan Marty and Kevin Wren, on the following problem. So suppose that you have a manifold and a d-dimensional manifold, and somebody sprinkles a lot of data points on the manifold, and then looks at all the pairwise geodesic distances on that manifold, and then corrupts those distances with noise. Okay, imagine that for every pair of points, the noise is independent of every other pair of points, but nevertheless, you are not told how the noise is produced, but you make some assumptions about it, like if the distance from A to B is less than the distance from C to D, then the expected noisy distance from A to B is going to be less than the expected noisy distance from C to D. You make a few assumptions like that. It then turns out to be possible to reconstruct the actual distances between the points much more accurately than you might guess, and therefore also reconstruct the geometry of the manifold. This builds on work by a team including, let me try to remember the names, Mati Lassos, a Finnish mathematician, Slava Kurilev, a Russian who unfortunately died an untimely death. Let's see, Hariharan again, and their postdocs, in which initially they assumed perfect knowledge of geodesic distances and solved the geometry problem of reconstructing the manifold. And what our group at Princeton did was to denoise the distances so that one could plug into that discovery. We discovered, I should say, that there is a group at MIT led by Elkanan Mussel, working on very, very, very closely related problems, and we, their group and ours have rediscovered the wheel. Let me think. Anything else? That's all that comes to mind at the moment.
Okay, thanks. And unless there are other questions or comments from the audience, I wanted to ask you about large language models. Somehow you use them, whether you use them as a source of inaccurate information, and yeah, imagine people usually pay to get better versions. You may pay to get worse versions. And then the second question is whether you how do you understand now, like if you see like the performance of the latest models released, and you see like this is a very personal question. You see, I look at neural networks and I understand them mathematically, right? And then okay, we'll take convolutional neural networks. Okay, everything that I can understand, I can reproduce. Say, but if I say, okay, I'm going to reproduce how any of these ChatGPT, Claude, this thing works, really like to get the feeling I would like to have as a mathematician, I'm not there. And I would like to ask you, are you there? Yeah.
Oh, okay. Well, first of all, I absolutely do not understand why large language models work so well. Absolutely not. I'm amazed by how well they work. It happens that last week I got an email from my friend, whom I think many of you know, Javi Gomez Serrano, who
Sure.
who produced I would say a joint paper by himself and Claude, okay, proving a theorem about a quantum mechanical system that Michael Weinstein and French mathematician Sonia Fliss and I studied in maybe 2022 or so. We were interested in zero energy solutions of some Hamiltonian, and Javi and Claude jointly produced a theorem giving estimates for the number of eigenvalues other than zero of the Hamiltonian. I am starting to read the paper. I wonder whether it is inaccurate information or whether it is correct. I've just begun, but so far it has made no obvious errors. And if it is correct, I would say that it's not an annals paper, but it could be safely accepted by, let's say, the communications in mathematical physics. Okay, so that's what AI can do now. I see no reason why further development should not put us all out of business. What are we actually going to do now? Let's say machines play, for example, chess better than any human, but I've read, I hope it's accurate information, that the strongest chess games are produced by, and so perhaps not in the not so perhaps in the near future, the strongest mathematics will be produced by teams like Javi and Claude. Now, of course, I could be wrong. First of all, maybe the joint work of Javi and Claude contains inaccurate information and it's not a proof. Maybe there will be some kind of hard limit. Maybe the large language model is very good at sort of putting together different things that people have, but to come up with anything that would really be called original at the highest level. I can actually see this in the current paper of Javi and Claude because it takes some tricks that we humans thought were restricted to the zero energy case and observes that sometimes they work in the non-zero energy case. So it gets, I would say, for originality, maybe it gets to B. But I don't know. I was very much impressed by an old documentary, AlphaGo. Okay, and of course this is very old AI, very low level AI by current standards. But it describes how AI played a game of Go, and for a while it was able to do pretty well. The European, but there was the snobbish assumption. Okay, fine, it can defeat the European champion, but the champion of Europe is not a serious player by Chinese or Korean standards, or Japanese, and for true originality, machines just can't hack it. And then, in fact, right, you know the rest. Well, you know maybe the whole story. If not, you can extrapolate. The machine came up with moves that were considered highly original. Now, Go is played on a board of, what is it, of 300 and some dots, and so the definition of a highly original move is an element of a set with 300 and some elements. That's, you know, math requires more dots. But I think it's a mistake to make the snobbish assumption that for true originality, a program is not going to get it. What do our minds do? Ultimately, they put together stuff that we've seen before. And well, computer programs do that too. We live in interesting times.
Very quick follow-up question. Say you are an editor in a journal at the level of communications in mathematical physics, and you receive that paper co-authored by Claude.
Yes.
Would you accept, like, do you see it? Well, first question is, would you accept it, push for it? And the second question is, would you see it accepted also by the other editors?
All right. So my own attitude is that I would like, at least at this stage, I would like to see it checked by a human. Okay. As long as it has been carefully checked by a human, and as long as the result is interesting, and as long as the contribution of AI is acknowledged, I would accept it. I'm reminded of an experience I had many years ago when I was an editor of the Annals, and somebody showed me a proof that what is it, that solving the P equals NP problem. And he wants to submit this to the Annals, but he warned me that he's going to put it on the World Wide Web, which was then a new thing. And would I accept it given that it had already appeared on the World Wide Web? And I thought about it, and I'm happy to say that I said, yes, I would accept it, even if it had previously appeared on the World Wide Web. Okay. Okay, let me go to another movie, having talked about AlphaGo. One of my current favorite movies is Hidden Figures, and there is a moment in which some calculation has been done by a computer, but NASA and John Glenn do not want to accept it until it has been verified by a human. So the assumption was that humans are more reliable at big numerical calculations than computers. And that was the way it was back in the day, no longer true. And I guess now humans and computers are both sources of inaccurate information. But I suppose that I can imagine, in response to your question, that maybe the day will come when an editor will say, well, all right, this has been refereed by humans, but has it been checked by a computer?
Yeah, actually, I wanted to ask about Lean and theorem provers, like Rock.
Yeah.
Like, have you had any experience with them? How do you regard them?
I am a fan of these things, but I have no personal experience with them. You see that I handwrite my slides. I'm very technical. But let's see. Okay, so I think Lean is a wonderful idea. I gather that it used to be extremely labor intensive to enter anything into Lean. There are now AI programs that enter stuff into Lean. I worry about the reliability of the AI programs that take the output of human effort and put it into Lean. I wonder, can one trust that? So I admire it. I mean, I think if the output of something has been checked by Lean, Lean has been produced by AI, for that matter, even by humans, because humans doing an awful lot of routine work tend to make mistakes. So I would still want a human referee signing off before accepting a paper to a journal. But again, I can imagine that will change as time goes on.
Okay, so if there are no more questions or comments, we thank you very much for the talk and for accepting our invitation. As you saw, as Joan said, in the department, you've been read since the 70s, and you could see at the beginning of the talk, they gather in a room like if this was the final of the World Cup to see your talk. So yeah, thanks a lot. We really appreciate that you joined us for this second.
I hope you enjoyed.
Yes, very much. And to everyone, we'll see you in 2027. This was the last of our talk this year. Okay. Thank you. See you next time.
Bye-bye.